When a physical system fails under stress, the breakdown rarely begins with a material defect. It traces back to a mathematical anomaly, a failing limit. On this Cartesian plane, a smooth curve represents a continuous function. Predictability requires that a function's actual value matches the expected value from its closest neighbors. We track the function approaching from the negative direction, the left-hand limit, and from the positive direction, the right-hand limit. A limit only exists if the left-hand limit and the right-hand limit converge to the exact same finite value. As long as this mathematical condition holds, the equations governing a structure remain unbroken. The physical systems built on those equations remain predictable and stable. But we must account for what happens to the system when that directional convergence fails. This fracture on the graph is a jump discontinuity. It is the specific mathematical event where the left-hand limit does not equal the right-hand limit. The values miss each other entirely. A mathematician might view this gap as an undefined coordinate, but for an engineer, this missing limit represents a physical boundary that must be managed. A jump discontinuity marks the point where airframes endure structural load spikes, digital logic triggers parasitic transients, and neural network optimization stalls. Consider an aircraft accelerating from subsonic to supersonic speeds. The fluid properties of the air around the wings undergo a rapid transition. Across a normal shockwave, air pressure, density, and flow velocity experience near instantaneous jumps in value. These properties do not change gradually. They shift across a localized boundary. Aerospace engineers deliberately model this shockwave as a true mathematical discontinuity. Treating the transition as a break in the limits is the most effective way to analyze the resulting forces. On this fluid dynamics cross-section, the shockwave is a stark vertical line. Aerodynamicists apply Rankine-Hugoniot conditions to evaluate differing pressures. Zooming into this macroscopic model reveals a microscopic scale where matter is continuous. Physical properties transition through millions of particle collisions, not a mathematical break. Despite this microscopic continuity, engineers must evaluate the one-sided limits at the macroscopic scale to design the airframe. By calculating the exact numerical gap between those one-sided limits, engineers can quantify the drag forces and structural loads that the aircraft must survive. In electronics engineering, we see a similar conflict between analytical models and hardware. Ideal digital circuits are modeled as operating in binary states of 0 and 1. Analytical models represent this binary switch using the Heaviside step function, depicting an instantaneous 90-degree jump from 0 to 5 volts. The left-hand limit is 0 volts, the right-hand limit is 5. This vertical gap implies an infinite rate of change, or infinite slew rate. Moving a voltage across a gap in 0 seconds is physically impossible. All physical hardware possesses parasitic capacitance and resistance that prevent instantaneous changes. These inherent properties force the voltage to change over a finite period of time. This actual voltage profile smooths the theoretical jump into a continuous differentiable curve. By evaluating the limit of this curve as time approaches infinity, engineers can establish precise clock cycle setup times and prevent high-frequency signal integrity failures. Training deep neural networks relies on a continuous landscape. The network minimizes loss through optimization algorithms that seek the lowest points in this space. To navigate these valleys, optimization algorithms require continuous derivatives, or gradients. These gradients provide the direction and magnitude needed to update the network's weights. Early neural networks were limited by their use of binary step functions as activation functions. On this loss landscape, you can see the flat plane of the step function. Because the plane is flat, its derivative is 0 everywhere, and it is undefined at the threshold. When a gradient hits that broken limit, the optimization process terminates. To solve this, computer scientists replaced discontinuous step functions with continuous approximations. Modern networks utilize activation functions like the rectified linear unit, or ReLU. With a continuous slope, the gradient descent vector can successfully move toward the minimum. Ensuring limits exist across these functions allows backpropagation gradients to flow through network layers without vanishing or becoming mathematically unstable. Analyzing these mathematical boundaries requires symbolic analysis. Engineers utilize Python libraries to build analytical environments, allowing them to calculate the behavior of limits before applying them to physical systems. Using tools like NumPy and Matplotlib, we can contrast continuous functions against piecewise models. We plot their convergence at a critical boundary coordinate, like x equals 2, to observe how the math behaves at the limit. These software simulations allow engineers to predict physical behaviors before building any hardware. Supersonic aerodynamics, signal propagation, and neural net optimization operate in different physical realms, but they are all governed by the same mathematical requirements for continuity. There is a constant tension between the ideal mathematical models we use to simplify the world and the continuous physical realities we must navigate. The numerical distance between a left-hand limit and a right-hand limit dictates how a system handles a transition, whether it is an air pressure spike or a voltage swing. For a mathematician, a failing limit is the end of a calculation. For an engineer, it is the starting point of design.